Thank you everyone for coming in here today. My name is Dr. Khalil, and I'll be discussing a broad range of projects that I've worked on during my research career. And I'd also like to thank GERAD for organizing these seminars and providing me with the opportunity to do so. As Professor Kokolaris mentioned, I worked in the systems optimization lab at McGill University, where I trained and received my doctorate degree, and have been working ever since as a postdoctoral researcher. But a little bit more background about me. I was also born and raised in the United Arab Emirates, where I received my bachelor's and master's education in mechanical engineering from Khalifa University. Today I'll be talking about a lot of different research projects that I've come across during my research career. And the general underlying theme, or what they all have in common, is some form of uncertainty. And that is the main aspect that they all try to address. So I started my research career about 9 years ago when I was doing my master's research. And it was in the energy sector at the time. And that was my first encounter with uncertainty in engineering design and operation. So I worked on oil and gas related projects, being in the energy sector. And what we noticed, and what motivated this research, is that these structures tended to fail prematurely sometimes due to fluctuations in operational conditions and most importantly, the environment in which they were placed. So the corrosion, because of the environment and the severe weather in the Middle East, were a main driver for these premature failures. So naturally, one way of mitigating uncertainty in these conditions, in these operational conditions, after having deployed and commissioned these pipelines, is to make measurements in order to reduce the level of uncertainty about when they are likely to fail. So we relied on instrumentation at the time in order to do so by placing periodic sensors along the length of the pipeline and monitor its structural health, so to speak. We relied on photonic sensors because they are intrinsically safe and they comply with oil and gas regulations. So the sensing principle was quite simple but potent. We used corrosion coupons that were stressed to begin with, so they had a non-zero stress field that increased over time as corrosion set in and the thickness got reduced, right? And what happens to the strain correspondingly is that it starts to decrease. And the rate at which mechanical strain decreased was proportional to the corrosion rate. And we verified that in a simulated lab environment where we controlled the corrosion rate manually by an electrical current. And when we switched it off, we noticed that the strain rate would stop decreasing and then continue to decrease linearly. So this is a very high-level overview of the project, but the main idea here is that, that is one approach of mitigating uncertainty that comes at a few costs. So for example, we have to put up some upfront cost into, purchasing the required instrumentation and retrofitting our assets or structures with these instruments. Of course, there are advances in the field that have, addressed this. But I will not be talking about them today. Anyway, that's not the main topic. And also, I want to mention that this is a reactive measure towards uncertainty. So these pipelines, for example, they weren't designed with sufficient corrosion tolerance to begin with, for example. So my doctorate degree focused on attacking this problem from a different perspective, all the way at the very beginning when, these assets didn't exist and they were just, in the early stages of their design. So I worked on a different application domain. In this case, it was the aerospace industry with our industrial collaborator, GKN Aerospace in Sweden. And they wanted to mitigate uncertainty that was brought about by the changing design requirements that mandated the design. So what GKN Aerospace does and does very well is that they manufacture aerostructural components for aero engines and aero engine original equipment manufacturers, such as Rolls-Royce, shown here. And one such structural component is the turbine rear frame. So this turbine rear frame has quite a relatively long life cycle of around 50 years, and a lot of changes can happen. So you can see that the uncertainty that we're working with here is a bit higher because we have a lot less information to work with. And the idea is that if you were to mitigate change, mitigate the change in requirements and its effect on your product, which is the turbine reframe in this case, if you were to build in sufficient tolerance against such change, like I mentioned earlier or alluded to earlier with the corrosion tolerance on pipelines, that would end up adding a lot of unnecessary weight sometimes if it's not utilized properly. And in the aerospace, something that is of major concern is the weight of the components. So we can see that our ability to mitigate change competes directly with the weight of the components. And if we were to look closely at this turbine rear frame, an example of change would be the thermal loads that it's subjected to because of the hot exhaust gases that go through it. If those loads were to increase, what we can do is passively absorb this change by building a sufficient margin or tolerance against said change. But another strategy that is becoming more and more viable these days is to absorb this change actively when it is needed. So we can now remanufacture and redesign these products to address changes as they occur, right? And this is more and more possible because of new technologies like additive manufacturing. For example, I can go ahead and deposit something on this component to stiffen it up, for example. Of course, there are a lot of decisions to be made with regards to how to manufacture this product and how to and when to redesign it or remanufacture it, and the manufacturing process parameters and so on. And naturally, this is a design optimization problem that is common in the industry. So this is what my doctorate degree focused on. I focused on both aspects of change mitigation in the design requirements as a means for reducing uncertainty in the design phases. So, of course, this also comes with a few advantages and disadvantages. The main disadvantage being is that uncertainty is much higher during the design stages and therefore cannot be completely eliminated. It can never be eliminated, but it can be minimized. And it also depends on your experience, your past knowledge. For example, GK Aerospace has been doing this for a long time, so they have an idea of what changes they're going to encounter. But if it's a new kind of innovative product, which we do not have enough a priori knowledge on, then this becomes more challenging. It also depends on our ability to explore many different designs. However, of course, this is a proactive measure, so we will end up putting up a higher capital investment cost upfront so that we do not have to retrofit or upgrade designs in the future. Right. So both of these problems featured change or uncertainty due to external factors or parameters. So they were like, the thermal loads or the operational conditions of the pipeline or the thermal loads experienced by the turbine rear frame. So they were all external to the system. But today I'll be talking about another source of uncertainty that comes from the models used in all of these engineering applications. So far, we've assumed that any measurement we make or any model, physics-based model that we use works more or less, provides values that are more or less reliable, right? But of course, all of these models and all of the measurements made using instruments, they have a certain level of uncertainty, right? So they have an inherent uncertainty in them. And that is the kind of uncertainty that we will be talking about today. The uncertainty due to the physical models used to describe these systems. And one such problem that is a good example of this are problems encountered in epidemiology. So towards the end of my doctorate and the beginning of my postdoctoral research, I worked with Professor Tokalaris on solving on solving decision-making problems that are pertinent to epidemiology, right? Using epidemiological models to inform those decisions. There are a number of challenges because these epidemiological models, they do not always provide reliable values or predictions. They provide a range of values that we have to work with. And they have a certain amount of uncertainty involved in them. So to better describe this situation or to better describe this aspect of epidemiology, I'll be going through a number of epidemiological models that are available in the literature. I'll provide a high-level overview of how they work. The most popular and common kind of epidemiological model is the compartmental model, where that consists of individuals that can have a number of states. So the states being, for example, whether the individual is susceptible to infection, or whether they are infected, or whether they are immune or recovered or dead, as given by fatality, right? So the transition between each of these states is governed by a transition probability. And at the individual level, at least, this results in a stochastic process. But in a population of individuals, we have a lot of interactions that can happen. And the behavior of the population, while it's causally dependent on the effect, the stochastic process that governs the individual, the population level trend can be approximated, right? So one way of doing so is to use compartmental epidemiological models, where we assume a homogeneous interaction between all the individuals. In other words, every individual in the system has an equal chance of interacting with every other individual in the system. And this assumption simplifies things a lot, because it allows us to calculate the population level response deterministically in the asymptotic limit when the number of individuals is large. So this response, given by the size of each compartment, where the compartment is, the membership of individuals to a particular state, evolves over time, right? So this is the response. And this response is governed by a number of ordinary differential equations, right? And their solution is well known and well documented. So keeping these features in mind, we can see there are a number of advantages and disadvantages to this kind of modeling approach. For example, the first advantage, the most obvious advantage, is that the solutions are analytically available and deterministic. So they can be computed with ease. And they capture large-scale population dynamics, all right? But the main shortcoming of this modeling strategy is that it does not account for geography, or more specifically, non-uniform population density, which is something that happens in real life. For example, if you look at the population density of Canada, we can see it's very sparsely populated, right? So what I mean by geography here is that if we were to look at this infected individual here, we can see that they have an equal chance of infecting every other individual, which is not necessarily the case. And because of this lack of ability to capture demographics and geography, we cannot model the effect or the efficacy of any intervention policies that we may apply to control the pandemic or the infection, right? So we can resort to a different kind of modeling approach. And these models are known as agent-based epidemiological models. They differ from compartmental models in two distinct ways. So the first way is that the interaction between individuals is heterogeneous. So only individuals that are within geographical proximity of one another can interact. And this results in a number of, so interactions are governed by a number of random events that can occur, which affect the stochastic process that governs an individual, right? So this is how heterogeneous interaction would work. Only nearby or geographically close individuals can interact. And if we were to look at the effect of this infected individual, you can see that they can only infect the ones that are in its immediate vicinity, right? And if we were to run this model for thousands of agents, for example, and potentially hundreds of thousands of agents, we would observe a response at the population level, but we would not be able to reproduce this response for different random seeds. What I mean by random seeds here is that is the random events that govern the interactions between individuals, the initial state of the model, so the initial conditions, and the way the demographics are distributed in the population. So for example, the age cohort of the different agents is distributed randomly at the beginning of any agent-based simulation. And if I change the random seed and draw another observation from the model, I will get another possible realization. right? So this is a slightly different outcome with the same parameters, right? But a different random seed. And if I look at the trajectory of the pandemic, which is the population level response shown here, this is the case for the first realization. And in the second realization, the number of infections was a little bit higher and the infection was, or the pandemic was more drawn out. And if I continue to draw observations, I will observe that the population level response is governed by a stochastic process, right? Which is shown here by the interquartile range. So with these features in mind for agent-based models, we can also list their advantages and disadvantages. Obviously, they account for geography and demographics, as I explained earlier. And this allows them to describe very localized phenomena at a high resolution. So things like outbreaks in schools, businesses, long-term care homes, and so on. But they do come with a few costs, right? Before I explain the cost, I will explain the most important feature that motivated us to use. I'm sorry? Yeah. So we will explain the most important feature that motivated us to use these models to begin with, and that is their ability to model intervention policies. So let's say we roll out a vaccination program, okay? And we vaccinate, the individuals surrounding this infected individual. So now these individuals become immune, for example, and we can see that we've already cut off the infection from the rest of the population, right? So this is what is known as herd immunity, right? And we've all heard of it because of the rollout of vaccination programs. So such an intervention can be modeled using agent-based modeling, which is difficult to account for in compartmental epidemiological models, right? So this is the main advantage of using them, but the main disadvantage is that, as I mentioned earlier, the response is stochastic. So when we do use these models to make decisions, we need to make sure that our decisions are applicable for every realization of the model, or at least a large number of realizations. And they are more computationally expensive to deploy. So they involve a lot of computations pertinent, to the interactions between individuals, and they do not involve as many assumptions or simplifying assumptions as their compartmental counterparts. So now that we've described and motivated the use of agent-based models, we come to the public health policy problem that we're trying to solve. So as I mentioned earlier, we can apply interventions to control the pandemic, but they do have a hidden cost, a cost that is sometimes overlooked by policymakers, and that is the socio-economic impact, right? So from trade theory, the mobility or the movement of individuals is thought of to be a proxy for economic output of a certain population or a certain demographic. So I will show you two cases to illustrate this. One is a case where no interventions are applied, shown on the left here. I will track the movement of one individual, shown in orange here, right? And the tracking will be done by counting the number of unique grids in the world that they have visited. And on the right here, I will show another example where some interventions are applied. By interventions, I mean controlling the number of essential workers that are able to traverse the population freely without any restrictions, the testing frequency used to identify and quarantine infected individuals, and some kind of social distancing measure. So if we let both scenarios play out, we'll see that although the number of infections was quite high here, and the fatalities were also high as a result, we can see that individuals are able to move more freely in this case than in the case with interventions. Of course, in this case, we have a lot less fatalities, although we do have a large number of infections, but we do have a lot less fatalities because they were isolated, they were treated in time, and they were not stuck out here outside the healthcare facility that I'm showing here. So we can see some kind of trade-off between intervention and socioeconomic impact or mobility of agents. And this trade-off is what motivated us to formulate a public health policy making problem. So if we were to look at the response in terms of the number of infections or the trajectory of the pandemic for the case with no interventions and the corresponding mobility, average mobility of the agents, we can see that applying interventions, although does reduce infections quite significantly, it does also hinder the mobility of agents. And this can be thought of as a proxy for a loss in productivity, in GDP, or in economic output. So we can formulate a problem where we wish to maximize the mobility of the agents and simultaneously reduce infections and keep them under control below a certain limit, right? And of course, the decisions that we need to make are in terms of, what kind of intervention policy we want to apply. So the number of essential workers that are allowed to traverse the population, the social distancing factor, and how frequently we test individuals. Now, this formulation of the problem is not complete because, as I mentioned earlier, these responses or these parameters of interest here are actually modeled by random, can be thought of as being modeled by random variables because they are the outputs of a stochastic process. So we do not know their exact values. We cannot ascertain them. So the model that is used here to guide, to allow us to calculate the objective and constraint is not only computationally expensive, does not provide gradient information, but is also noisy. Of agents. I'm sorry, maximize in this case. So this expected value is going to be our proxy for what the objective function should be. And the expected value cannot be calculated exactly. It can be approximated by using estimates. So we can draw different observations from the black box and use the mean to estimate the expected value of the objective. Same thing can be done for the constraints. And these variables that govern or affect the values of the objective and constraints, they are related to the initial conditions that were used for the simulation. They are related to the interactions between individuals, the distribution of demographics, and so on. So before solving this problem, and for the sake of completeness, I'll provide you with an overview of the algorithm that we use to solve this problem. Now, I want to mention that I'm not the developer of any of these optimization algorithms, but I'm providing a high-level overview of how they work here for the sake of completeness. So I will tackle the first kind of problem where the black box is expensive to evaluate and does not provide gradient information, right? So when we have such a problem at our hands, a class of derivative-free optimization algorithms can be used to solve such problems. And one such method is the mesh adaptive direct search algorithm, which has been developed by colleagues at GERAD and others. So this algorithm involves a search step, which is optional, and a poll step. And we will be focusing on the poll step here because the convergence properties of this algorithm apply in the poll step, or it's the poll step that imbues this algorithm with local convergence properties. So the algorithm discretizes the space of variables, and this discretization is referred to as the mesh. And it simultaneously constructs a frame in the poll step shown by this dark or thick bordered black box here. And what we do is that in this frame, we evaluate, or at the center of this frame lies the incumbent solution. And the frame is also simultaneously used to construct or to obtain a set of trial points from something that is known as the polling directions. So these trial points and incumbent solution describe the evaluations that will be made in the poll step. So the objective function value is evaluated at each one of these points. And if none of the trial points offer an improvement in the objective relative to the incumbent solution, then the poll step is called a failure. And although failure has a negative connotation associated with it, the word failure, it just means that, at least in this current frame, the local optimum is at the incumbent. So it's the failure in the poll step will result in the algorithm reducing the mesh size and corresponding frame, as shown here. And repeated evaluation of the trial points and the incumbent solution will be used to ascertain if this is a failure or not. And if it fails again, then the mesh size is reduced even further, and so on. But if one of the trial points does happen to provide an improvement in the objective function value, then this poll step is called a success, and the frame size is increased, and this new frame is centered at that trial point that was successful, which now becomes the incumbent solution. And successive failures will cause the algorithm to decrease the mesh size until a certain minimum mesh size is reached, which is used to terminate the algorithm. So far I've talked about, evaluating the objective at the trial points and the incumbent solution. But I haven't talked about the case when, the objective is governed by a noisy black box. So we cannot assume that, one observation from the black box is the actual value of the objective at the incumbent and trial points. Instead, we construct estimates at each one of these points by taking the mean of several observations, and then commit these to the algorithm in order to ascertain whether, the pulse step is successful or not. But the number of samples that are drawn in order to construct the estimates is itself an algorithmic parameter. But what this algorithm does is also simultaneously keeps track of the uncertainty in these estimates. So in this case, I'm showing a region surrounding the incumbent that describes the uncertainty in the estimated objective function value. I have to stress that this region is not necessarily a circle or a sphere. It's arbitrarily shaped in reality, but I'm using a circle for the sake of demonstration. And any trial point evaluated from within this region will not provide a sufficient change in the objective function because of the noise in the black box, right? Only when only when there is a sufficient decrease in the objective function that corresponds to a decrease in the actual true or latent objective function will that change be considered certain, right? So if all the other trial points relative to the incumbent happen to lie beyond this uncertainty interval, or provide objective function values that are beyond the uncertainty interval, then the pole step is deemed a certain failure, and the mesh size is reduced aggressively in order to evaluate more trial points in the vicinity of the incumbent. But if any of the trial points happen to lie within this uncertainty interval, then the mesh size is reduced less aggressively in order to gradually reduce the uncertainty in the estimates, and so on. And as with the deterministic counterpart of this algorithm, the algorithm terminates when a certain minimum mesh size is reached. So this is a high-level overview of how the stochastic variant of mesh adaptive direct search works, and has been developed by my colleagues at GERAD, namely Professor Charles Audet, Professor Sebastian Ledegabel, and Dr. Joseph Zahini, and Professor Michael Kokolaris. And they even worked on extending this algorithm for constraint optimization problems. So far, I haven't even talked about the constraints. So there is a variant of this algorithm, StoMADS PB, which handles constraints using the progressive barrier approach, and is currently in the process of being reviewed and published. So going back to the original problem, and with this information in mind about stochastic mesh adaptive direct search, we solve the problem not only using StoMADS or stochastic MADS, but we also solve it using its deterministic counterpart, MADS, as given by the NOMAD implementation of it, which is an open source software provided by GERAD as well, and genetic algorithms, which are very well known and widely popular. So this is how the solution evolves as we evaluate the black box using the StoMADS algorithm. And we can see that it does converge locally to a minimum objective function value shown here. We allow the other algorithms for a fair comparison to sample as many times as StoMADS did. So 4 times in this case, in order to provide a fair comparison. And this is the result for the NOMAD algorithm. We can see that it did offer a better objective function value, but we will wait a little bit before calling this a victory for NOMAD. So the genetic algorithm converts to a relatively suboptimal solution with respect to the other 2 algorithms. If we look at the constraint function and how constraint violation evolved over time, we can see that overall the NOMAD algorithm had higher constraint violation compared to StoMADS. And although they look quite closely matched here, the difference between them is huge in terms of the variance in the objective function. So I'm going to show you an example now to illustrate this. But first, a comment on the genetic algorithm. We can see that it shows a very conservative solution when it came to the constraint. And the reason that all of these algorithms are converging to the point where we have zero constraint violation, or where the constraint function is evaluates to zero, is that it is an active constraint. So the optimum lies when the constraint is active. So if we were to look at the constraint function, which is the number of infections, and this is the threshold shown here for the constraint, which is given by the healthcare capacity, we can see that the StoMADS algorithm was well within the constraint for every possible realization of the black box. The genetic algorithm obviously chose a more conservative approach, but the NOMAD algorithm, although the median does lie within the constraint bounds, there are a few realizations that caused the pandemic to grow out of control very quickly. Because once healthcare capacity is exceeded, there's no more room to treat sick individuals or isolate them. So we can see that in conclusion, the StoMADS algorithm performed well on problems with active constraints. And the objective function value, we can see that although there's not much of a difference between the StoMADS solution and the NOMAD solution, we can see the difference was quite huge in terms of the variance. And that is the part that NOMAD could not handle. So we managed to identify optimal public health policies using a number of optimization algorithms in this work. They favored high testing capacity, which is something that some countries have done very successfully. A large number of essential workers to keep economic output at acceptable levels, and a modest amount of social distancing to allow herd immunity effects to take place once infections start to set in slowly but surely. And StoMADS did well on problems with active constraints, at least on this problem. But more objective benchmark studies could be done, for example, by constructing the appropriate data profiles needed to evaluate the performance of these algorithms on different problems. And we've also even managed to apply the algorithm to solve pertinent public health policy problems using other agent-based models that are in the literature. So this is an example of one such model that has been developed by a team in Imperial College and has been used partly to guide policy making in the United Kingdom. So this model was also subject to the same kind of uncertainty as the agent-based model that I showed. So it did result in a stochastic process that describes the evolution of the pandemic. And it is also a good problem to be solved using stochastic derivative-free algorithms. I want to mention also that continuous control of these intervention policies, so such as the number of essential workers, social distancing, and the testing capacity, can also be achieved using optimal control theory. So in more general settings, it can be done using algorithms like reinforcement learning, which are well suited for continuous control of stochastic processes. And that is something that could be done in the future. I'll also be talking about another interesting application of stochastic derivative-free optimization today that is also pertinent to COVID-19 and the pandemic. While the previous study was general to many different pandemics that could arise, this one is more specific to COVID-19, and it involves the field of machine learning. So in this work, I collaborated with a former colleague of mine at the Systems Optimization Lab, who is now at Harvard Medical School and Massachusetts General Hospital, and another colleague of mine who is now at Ohio State University, on developing a machine learning model for nowcasting the COVID-19 pandemic trajectory. So by nowcasting, I mean providing a short-term prediction of the incidence rate of the pandemic. We had access to some data from a hospital in Lebanon, the Rafik Hariri University Hospital, and from that hospital, the data that we had access to was pertinent to the patients. So we had a cohort of patients who came in for their PCR tests, which we all know that are used as the golden standard for diagnosing COVID-19. And what these tests tell us is these tests do not only provide the diagnosis, but they also provide a measure of the viral load in the individual. So we can see that the average viral load in the cohort of patients increased over time as the incidence rate increased. So this viral load is given by a value known as CT, which is inversely proportional to it. So we can see that high peaks in viral load correspond to delayed peaks in the incidence rates. And we figured that these two pieces of information, they could become features to train a machine learning model for predicting the future incidence rates. So we used a model known as a seek-to-seek model, which is a common model used in natural language processing applications and translation and time series forecasting, where it takes a set of values or a time series as its input and outputs another time series of a different length. It's based on recurrent neural networks, which are well suited to deal with systems that involve time series and how they evolve as well. So the main distinct factor here is that recurrent neural networks, they account for the fact that data points that are closer together temporally are actually not independent of one another, right? Which is the main assumption made during supervised learning, is that all training points should be identically and independently distributed. So this model is based on recurrent neural networks. So we input these two features as a time series so over the past few days. So the number of days over which this time series is formed is known as the sliding window. And we have to decide on its length as part of the design of this network. And we have to decide also on the number of layers, should we wish to identify high-level feature interactions between these two parameters. And this itself is a kind of design problem, the development of machine learning algorithms and their architecture. So one such problem or one such design problem that is usually pertinent in the machine learning literature is known as hyperparameter optimization, where we choose, where we have to decide on the different parameters that govern the structure of the model. There are very well accepted ways to do so for certain hyperparameters, such as the number of epochs, where, for example, something with a concept known as early stopping can be used to terminate the training of deep neural networks by backpropagation when a local minimum in the validation error has been reached, right? So this is a form of regularization meant to reduce overfitting. So what we do is we make a checkpoint here, and then we select that model as the final model of the training of the backpropagation process. But there are other hyperparameters that we also need to tune. So not everything can be tuned using this way. We have to worry about things like the dropout rate, for example, which is another way to regularize deep neural networks by assigning them lower weights and biases that would essentially help them generalize better, by dropping certain neurons from the network, or the batch size used during training, or the activation functions of the neurons themselves. And backpropagation of deep neural networks or training itself can be expensive. It could involve several GPUs. Backpropagation itself is a stochastic process, right? Because it does involve some random search steps, especially when algorithms like Adam or stochastic gradient descent are used in backpropagation. So we can see that this problem has a few similar traits to the one I described earlier. So if we were to look at this sliding window parameter that I described earlier, the number of days in the past used to construct the input time series, if we had 1 day as that parameter and we observed the validation error simultaneously, we can see that if we repeatedly run the training algorithm several times, we'll get a distribution of values for the validation error because of the stochasticity that I described earlier. And as we increase the number of days, we are able to capture more information. So we have more temporal information now in our input time series, which results in a reduction on the overall validation error or its expected value. And if we increase it again, we can see that the error starts to climb again and increase again and then decline once more, and so on. And we can see that this problem has a global optimum at 6 and has several other local optima, right? And the objective function value of interest here, the validation error, is also stochastic, or is given by, can be modeled by a random variable. And this applies for also other hyperparameters, such as the number of hidden neurons, the probability of dropout or the dropout rate, to name a few. So we can formulate this as an optimization problem or a stochastic optimization problem, where we want to minimize the expected value of the cross-validation error and decide on the hyperparameters. And the randomness or the stochasticity is a result of the weights and biases that are used to initialize all the learnable parameters in the network, the gradient descent algorithm itself, and so on. So we solved this optimization problem to obtain a good model that generalizes well even on unseen data. And we also realized that, a byproduct of the study is that, of course, which is the main factor that motivated the study, is that, the viral load measurements that were taken from the patients were a very useful feature for improving, the nowcasting performance of this model, right? So the result of this optimization of hyperparameters resulted in a model that also generalizes well on unseen data. So after developing all of these models, we managed to solicit 4 months of additional data. And then we applied, the trained algorithm and used it to make predictions in these 4 months. And we managed to generalize well even on unseen data. Of course, we also applied it to other similar data sets, but its efficacy was dependent on the way that data was solicited and collected. For example, the PCR tests were collected in a different manner that we did not have. So in our data set, so these assumptions, or more accurately to say, the assumptions of the underlying data set should be applicable in every setting that the model is applied to, right? And this data set that we tried the model on came from another team in Harvard Medical School that developed a Bayesian inference framework for, nowcasting the pandemic trajectory using viral load measurements. But besides that, what I want to mention and stress is that, the problem that I formulated earlier in terms of hyperparameter optimization can be extended. So for example, we can introduce a constraint here on the complexity of the model, right? And by complexity, I mean the number of learnable parameters, which directly influences the inference time of this model, right? So for example, in Internet of Things applications or edge computing applications, we really care about the ability of these models to provide predictions in real time, and they need to be lightweight in terms of how much CPU resources do they need and how much memory do they need. So this can be set as a constraint to the hyperparameter problem and solved. And I put it here as a deterministic constraint because unlike the validation error or the performance of the model, it can be a deterministic value. And most importantly, that this kind of hyperparameter optimization should be benchmarked against state-of-the-art methods. So this has not been done yet. So other algorithms such as HyperNomad, which is also developed at GERAD, or Bayesian optimization, which is the standard for conducting hyperparameter optimization, should be used as a benchmark. And of course, a mixed variable version of StoMADS is needed to address a wide range of hyperparameter problems. Sorry, the lights went out. But anyway, so a mixed variable version of StoMADS is needed in order to address a wide range of hyperparameter problems where, the hyperparameter could come from a non-ordinal categorical variable, for example, right? So in summary, we've looked at problems where the uncertainty in the model was endogenous, right? Or it came from the models themselves. And what all of these problems had in common is that they involved computationally expensive function evaluations and limited or no gradient information available, and a high dimensional space of variables that we needed to decide on, and they were of mixed types. So they could have been ordinal, continuous, or categorical, etc. And just to allude to future work that I'm working on right now with Chalmers University and my collaborators there, is that we're working on an exciting project that is actually involving both kinds of uncertainty. For example, the uncertainty due to the external parameters and the models used in the simulations and so on will be accounted for. And I hope to be able to present it in future seminars and talks at GERAD as well when it is ready. So thank you very much for listening in today, and I'll be happy to receive any questions you have. I hope I left you with more answers than questions and less uncertainty, at least about what I do at GERAD. So thank you.
Thank you very much, Khalil. That was a very broad talk that I enjoyed, seeing you summarizing so much work in so little time.